Hello peeps! Our topic is relative velocity. We've got a situation here where we've got car 1 in blue, car 2 in red. Car 1 is traveling at velocity v1. It's faster than v2. This vector arrow is longer, therefore representing higher velocity than the shorter arrow of v2, yet v2 has a head start of h. And so what we're going to try to figure out is when car v1 catches up to car v2. We're going to model that algebraically, but to do so, we look at a couple of modeling equations that describe the motion of each car. These come from position versus time graphs, actually. So if we start at the origin, there's no y-intercept. So the modeling equation, number 1 here, for car number 1, is x1 equals v1 times t. v1 being the velocity, which is the slope of the position versus time graph for that car, okay? And then for car 2, we have x2 equals v2 times time plus h. h is the head start and is represented by the y-intercept. v2 is also a slope on the position versus time graph. However, it's going to be slower and not as steep on that graph. So these are two separate equations of lines and two graphs that would be superimposed on one graph. This has a y-intercept, car number 2. Car number 1 will have a steeper slope. Well, here's our prompt. What we've got is, at what position does car 1 meet and pass car 2? Well, what we can think of is that they meet when each car reaches the same position, okay? That makes sense. When they meet, they're going to be at the same position relative to the origin. So that's going to be a clue because it's going to allow us to solve for this algebraically, because that means we're going to set x1 equals x2. Both positions are going to be the same. And so when I do that, I've got x1 equals v1 times t, x2 equals v2 times t plus h. These two expressions equal each other, so that's what I've done over here. v1 times t equals v2 times t plus h. So we solve for t and find when they meet. So we actually get the when part first. That's the time, and then we can find where. So we do some algebra and we solve for t. We use the rules of algebra. And t equals h divided by v1 minus v2. Notice that in the denominator I've got parentheses because it's always safer to handle the denominator when you encase it in parentheses, particularly when you're doing the calculation, because without parentheses you may screw up some of the operations. Okay, so that's why I do that here. v1 minus v2, as you remember from frames of reference, is actually the relative velocity between car 1 and car 2. So we'll see that when we actually do an example with numbers. That will become more apparent what this means, that v1 minus v2 is the relative velocity between the two cars. So what we do with this t is plug this expression back into equation 1. Equation 1 is right here. See, this is the t. So now it's x1 equals v1 times that expression, which is h divided by v1 minus v2. And so here it is, x equals v1 times h over v1 minus v2. We have a finalized algebraic expression that we can now use if we know the velocity of each car and we know the head start. We can now determine at what position they will meet. Let's do some examples. Relative velocity examples, 2 cases. Case number 1, it's the one we described before, but now we've got some numbers attached to it, okay? v1 is faster than v2, the head start is h. They're both going in the same direction. Where does v1 catch v2? Okay, v1 is 5 meters per second, v2 is 2 meters per second, and this h, let's call it 9 meters. So we use the expression, the general expression over here, to find the displacement from the origin. And we get x equals 5 meters per second times 9 meters, the head start, over the denominator 5 meters per second minus 2 meters per second. So the denominator is 3. And what we get is position 15. Okay, that makes a lot of sense because if we think about this in terms of relative velocity, which is helpful right now if we consider these numbers over here, I mentioned that v1 minus v2 is the relative velocity. Okay, so let's change frames of reference for just a moment, okay? So v1 V1 is catching up to, is faster than V2. Well, how much faster? It's 3 meters per second faster, 5 minus 2. So every second that goes by, V1 will make up 3 meters. So the relative velocity, if we were to say the frame of reference over here of V2 were 0, how quickly is V1 catching up? It's catching up at 3 meters per second. That's what this says. That's what this says. So we can think of it this way. If this were standing still and this car were coming at it at 3 meters per second, and the distance over here were 9 meters, it would take 3 seconds to close this gap. Okay, 3 seconds to close this gap in that frame of reference. Well, if it takes 3 seconds and we go back into the frame of reference where this is moving at 5 meters per second, 3 times 5 is 15. So you can think about it that way in terms of this difference. You can set 1 to 0, like V2, and consider, well, if this is 0, that means V1 would be approaching it at 3 meters per second. It's helpful to do that sometimes, more complex examples, and we'll tend to do that later on this year. Let's look at case number 2. What we've got is 2 cars colliding with each other. This is a smash 'em up derby. So V1 is 5 meters per second, still the same, but now V2, which is 2 meters per second, but it's going in the negative direction. It's going to the left, okay? And they're separated by a distance h. And so what I created over here was V1 is 5 meters per second, V2 is negative 2 meters per second, h was 14 meters. The separation is 14 meters. Where are they going to meet? Okay, and let's consider this to be the origin over here. That would be relative to V1. This is how this is derived. X equals 5 meters per second, times 14 meters, that's the h, the separation, and we have 5 meters per second minus negative 2 meters per second. Oh, this becomes a plus sign over here pretty much, minus a negative is plus. So we have 5 times 14 divided by 7, that's the same thing as 5 times 2, or 10 meters. So these two will meet at position 10 meters, which is 10 meters away from car number 1, and that'd be 4 meters away from car 2. Let's look at it from the relative velocity perspective once again. All right, well, if we were to, for example, set car 2 equals to 0, okay, we can change our frame of reference. We take the frame of reference of car 2. It looks like car 1 is approaching it at 7 meters per second, because when 2 vehicles come at each other, those velocities would add because one of them is negative, okay? So if, in this case, we have a situation where this is 0 and car 1 would be coming at a stationary object at 7 meters per second, the addition of these two coming at each other, then it would take 2 seconds for car 1 to reach this location. It would travel 7 meters and then another 7 meters, and then that's it. So if it travels for 2 seconds, well, what's the position going back to the original frame of reference? 2 seconds times 5 meters per second. Well, 5 meters 1 second, 5 meters the other second, and we get to 10 meters, okay? So we can work it and rationalize it using relative velocity, but of course this algebraic formula, the end result, will work just as well. It's just nice to think about things and represent them in a few different ways. And so that's it. That's relative velocity. Now we can put it into practice and check out them cars moving to and fro. All right, beautiful stuff. Morad out.